You are listening to the Unusually Well-Informed podcast.
Welcome to the Unusually Well-Informed podcast. I'm your host, Tim Hampton. My unusually well-informed guest today is Dr. George Zhu. George is a professor at the Lassonde School of Engineering at York University. He is also a research chair in space technology and director of the Space Engineering Design Laboratory. George has published over 300 journal and conference papers and is internationally acknowledged as a leader in astronautics, spacecraft dynamics and control, and space debris mitigation. Today, George and I are going to discuss his research projects and the exciting possibilities they create. George, welcome to the show.
Thank you, Jim. Thank you for having me with you in the show. I'm excited about sharing my story about the space, anything about space.
Thank you. It's my pleasure. So let me begin with the DESCENT project, which I understand is deorbiting spacecraft with electrodynamic tethers. How does that work?
Oh, DESCENT represent, it's a long word. We call the deorbit space debris using electrodynamic tether. So before we start, just give you some little background about electrodynamic tether. So electrodynamic tether is a very long, thin, electrically conductive tether in the space. So when it moving along, orbiting in the Earth's orbit, it will cut the magnetic field, or we call the magnetic line of the Earth's magnetic field. And because of the Lorentz law, that Lorentz force will push the free electrons in the metal tether and then make a charge. It just push electron to one end and the ions to the other end. And so if you add a electron image at one end that collect all the electrons pushed by those Lorentz force, and you push it back into the Earth's like the ambient. It's not the true vacuum, because in the low Earth orbit, there's a lot of plasma. So it's like you submerge into a sea of plasma. There's a lot of free electrons. So you shoot the electron back into that plasma and then form the current within your electrical wires. Then you know that like electric motor, right? You have the conductive wires moving in the electric field, magnetic field. It will generate a force against their motion. So that's how it works. So, but until now, this concept is only in the drawing board. People think, oh, we can use that, we call it electrical drag, to push the space debris down to the Earth, right? Because it's you add the drag against its motion to accelerate its deorbiting process. But it has never been tested. Mm-hmm. So our mission is about to demonstrate this concept, and it actually works. So the DESCENT mission is built with two Cubesat. Each Cubesat is a 10 by 10 by 10 centimeters. And then we stored 100-meter tether. It's a very thin aluminum coil, right, inside the one Cubesat. And the two Cubesat was tied together before launch. And once it's shoot into the orbit, then once it's established communication with the Earth station, Earth ground station, we will send a command to separate that to satellite, and then we can demonstrate the theory. So far, we have launched that Cubesat into orbit, I think in the November 5th, 2020.
Okay.
And now we operate that Cubesat for almost 10 months.
Hmm.
Yeah. We did a bunch of the tests, and we tried to deploy the tether, but it is always the tough part to separate the two satellites and deploy the tether.
Yes.
If you look into the history of the tether satellite, well, 60% of the mission failed to deploy the tether. And that bad luck happened to ours, our mission.
See. So
we won't be able to separate.
Let me follow up on a couple of the concepts there. So the Earth has a magnetic field. I understand is because there's a molten iron core that's rotating relative to the Earth, because the Earth is rotating around it.
Yeah.
And that generates an electric field, as you say, like a motor. And then the wire itself interacts with that. And there's a couple of concepts I want to explore. One is, okay, so in the descent project, you had two very similar CubeSats intended to be at either end.
Yeah.
And the drag that's produced by the magnetic field interacting with the wire is going to be somewhat equal on the whole length of the wire.
No.
Not true? No?
Not true. It depends. There's two types of electrodynamic tether system.
Okay.
One is you have the insulate electrical wire tether. Then your electron collectors or emitters on both ends. So you have the constant current generated along the tether. So then in that case, the Lorentz force, we call electric drag, is equal along the tether.
Okay.
There's another concept. They use we call the bare tether. So means the tether is not electrically insulated.
Mm-hmm.
So the tether itself, it was served as a electron collector because when you're moving along, the magnetic field will push the electron negative charge to the lower end. So if you manage it to control the potential bias at the lower end, then the whole tether will be positively biased relative to the environment plasma. So that tether itself becomes electron attractor. So in that case, at the very top, it attracts a little bit electrons. At the very bottom, it's attracted because accumulated along the tether. It attracts a lot of electrons. So the electric current is going from zero to the maximum at the bottom. So the force is not equally distributed along the tether.
So I will confess I'm a mechanical engineer. My electrical stuff is pretty weak. But is the wire interacting, or are you collecting the electrons and intending to emit them in a way that generates force?
Yeah, the wire is moving. So when it's moving, it cuts the magnetic field, and then it generates the bias. So in the second approach, we save one electron contact by using the positively biased tether as an electron collector. Because it's a positive bias, it will attract the free electrons from environmental plasma to the tether. Then at the bottom, because once the electrons touch the tether or get very close to the tether, it will be attracted by those Columbus law and go to the tether. And then the Lorentz force, because of the motion of the tether, will push that electron tether down to the bottom. Then we have the electron collector collect and shoot it back into the atmosphere.
So a follow-up question on that then is, would it only work in low Earth orbit? Like if we get further away from the Earth, we are still in the magnetic field, but there's less plasma to use?
Yes, you are absolutely right. The plasma density drops as the altitude increased. So the plasma density, according to our current knowledge, peaked at about 400 kilometers above the ground. Then if you reach to the 1,000 kilometers or the 1,200 kilometers, then the electron density is almost zero. So that's upper limit. Usually
it's only useful close to the atmosphere. So let's talk about some possibilities as far as practical use of this. One is to deorbit, as you spoke about earlier, it's deorbiting debris. Why is orbital debris a problem?
Yeah, the orbital debris, because you imagine orbital debris is moving on the orbit, right, at a very high speed. So if the two pieces moving relatively in this way, and their speed will be up to 15 kilometers per second, because the first what you call the speed to escape the Earth's gravity is 7.9 kilometers, right, per second. So if you have a lot of those debris there, so it will have the potential to hit the other satellite or other debris. So give you some statistics. Since the first satellite into the orbit in 50s, now we have the US constantly monitor that. So we have about 30,000 pieces of debris, which is larger than 10 centimeters. Large. And big. And big. And between the 10 centimeter to 5 centimeters, there's another probably 20,000. Anything below 5 centimeters is non-traceable now. So the estimate number will be around 500,000 to 1 million. So the chance to be hit by debris is very high.
Yeah. And the smaller pieces, of course, are not complete satellites. These are, you could think of them as accidental fragments of failed missions or things that are disposed of during, like let's say you have stage separation, you have explosive bolts, that kind of thing.
Yeah. And even paint, the paint.
Yeah. You wouldn't want to get hit by a paint chip at 15 kilometers per second.
You don't want.
No. Well, then how in your imagination, as you look forward to this technology of using the Lorentz force to slow down debris and burn it up into the atmosphere, how would a tethered system attach to that debris? You'd have to have some sort of robotic.
Yeah, there's a two ways. One is it's the current that I work is a design standalone system that can be attached to a new satellite. So when they reach the end of the mission stage, they just deploy that, and they will pull it back.
Like throwing an anchor out.
Yeah. Anchor to the thick atmosphere, right? Like you can imagine this way. The second way is, you are right. So we have to use the we call it space robotic to capture debris or dead satellite, then attach that device to that object, and then deploy the tether. Then you can decelerate. The deorbit this debris. And
that would be an extremely slow process to deal with millions of bits of hardware in space.
Yes. So economically, people look in that way. People think the NASA scientists did the simulation 10 years ago. Say, in order to address the space debris issue, the first thing, let's stop the increasing trend. In order to do that, every year we only need to remove 5 big pieces, say several tons of the large debris. Then you can stop the increased trend, because the large piece will kind of defragment, the impact with another debris will generate more debris.
Yeah, is that called the Kessler syndrome?
Syndrome?
What do you call it?
Kessler syndrome.
Kessler.
Yep.
And the idea is that one object blowing up it's almost like nuclear fission, right? You've got debris everywhere in orbit and causing a chain reaction.
It's like a cascade chain reaction.
Yeah, terrible. Let me ask you if when we're in orbit, we have solar power, we have a lot of electricity at our disposal. Can we use a tether to accelerate to a higher or preferred orbit somehow? Can we use the force? Can we interact with the tether and the magnetism to go higher?
Yes, theoretically, it is possible, because the way I'm talking about before, we call the generating mode. So basically, we convert kinetic energy of the debris or satellite into electricity and the heat dissipated. So as a cost, because the energy is conserved. So we would convert kinetic energy into heat dissipated. So you lose the orbital height. On the other way, so we need to import energy into that system. So we basically put a power source. The power can come from a sun or come from nuclear reactor. And then we reverse the current. So if say we current go this way, we generate the Lorentz force is against motion. So imagine if we reverse, we put the another high voltage powers to reverse the electricity directions, then the Lorentz force is in line with the motion. In that way, you can actually boost your orbit. So interesting you mentioned that one. The electrodynamic tether was first developed to boost the orbit of the International Space Station instead of you burn the fuel.
So that was what it was. What it was. There was a theory they could use that, or did they use it for that use?
This technology was originally developed for that purpose. It's in 1980s, and then NASA did 2 large-scale electrodynamic tether mission. It's a 20 kilometers tether in 1993, and unfortunately, 2 missions both were failed. One was failed to deploy the tether. The other one deployed the 20 kilometers of tether, and the tether was cut by an electrical arc.
Oh, yes, I can imagine.
Because they're highly charged, the tether, and the space shuttle, it's a metal ground, and you have a conductive medium with a plasma. So because of that, the NASA think this technology is high risk.
Yeah.
So, yeah.
What if it did work? Can it only accelerate me on my current path, or can I have an arbitrary control over which direction I accelerate?
Yes, you can, because you control the current density, right? You regulate the current, then you can control the force.
The force, but not the direction, or can I control the direction?
Direction, no.
Okay, so I can control how much I go, but I can't control. Okay.
And also, just to let you know, for satellite maneuvering in the space, we usually maneuver the satellite within the orbital plane. Because based on the orbital dynamics, if you want to maneuver the satellite from one orbital plane to another orbital plane, it costs too much. It requires huge energy. Yeah. So you're better off maybe launch a new satellite to a new orbital plane. It costs less.
Well, I was wondering about that because you have these huge constellations now, like SpaceX is launching. Starlink. And they have 60 satellites or I think it's 60 or 80 satellites in one launch. They have to diverge a little bit over time, right?
Yeah, but they are all within a one orbital plane.
I see.
So the orbital height may change because of the drag, but they will stick in that plane. They won't go to other plane.
Okay. So you mentioned that the descent experiment was a CubeSat. Can we talk a little bit about CubeSats? What are CubeSats and what are the advantages of CubeSats?
Yeah, the CubeSat concept was first developed by I think the University of California in Los Angeles, and they want to cut the cost, because in the past the cost for satellite is so high because everything's customer made and the high quality requirement. So they say, okay, let's develop a standard. The CubeSat means one cube. They have the unit 1U. They call it 1 cube. It's a 10 centimeter cube. So if you need 2U, we call it 2U. You stack up them together. So they standardized that design, and then everybody, so they can have different companies specialize on one component, but following that standard. So that created a way for university students to be able to build and launch the satellite. So that it's an economical way. So originally it's designed for education only. But now the big company like Lockheed Martin, those NASA, they see the commercial value of that. So more and more they use the CubeSat as a test platform to demonstrate some new device.
And the advantage, of course, is that if you have a standard form factor, then it's almost like Tetris. You can pack a lot of satellites into one nose cone.
Yes,
and you know that really you just need to worry about the weight and the
volume.
size.
Yeah.
How are they deployed? There must be a variety of ways they're deployed.
There's a lot of ways to deploy. One way is for the big launch satellite, for the rocket. At the end, they always need some ballast weight to make sure the CG is in the ideal position. Right. So to do that, they will put some ballast weight around the rocket. So those big companies, they sell those space to CubeSat or even the small nanosat. And this is one way. And now there's a special company just for CubeSat. So they designed a rocket that can launch probably 20, 30, 100 CubeSat. India is very successful at have launched with this launch vehicle. It's a commercial model. The other way is you have the standard port. Everybody put your CubeSat into a standard port. And then you ship the CubeSat with the port. And then the port they put in the rocket, launch it, or you send your port into the International Space Station. And from there, the astronauts activate the deployment. So for our descent mission, we use the last option.
And the company you're referring to, is that NanoRacks?
Yes, it's a NanoRack. They signed a contract with the NASA to mainly service to the education institution, university.
I see.
To provide those services.
One of the exciting things is, when we look at satellites being built, at least in the older videos and older pictures, it's people with white hats and white gloves, and it's in a very clean facility and everything. It's very sort of particular. It's expensive. But a CubeSat, you can make it out of off-the-shelf components. You can use bits and pieces from a phone. You can use a Raspberry Pi. How was the descent module put together? Where did you get the parts for that?
We have a 2 cube. So we did some experiment, as you mentioned. For 1 cube, it's most important. And we bought the components from this company. They have a space heritage, means the similar products has been tested in the space. So those components had a very high reliability,
Right.
but the cost is huge. And
Yes.
the other cube, we use the commercial of
Oh,
the share of components like a Raspberry Pi. Basically, we use a Raspberry Pi as the onboard computer. I give you the comparison. The Raspberry Pi costs 30 to 50 US dollars.
yes.
And it's much powerful. And onboard computer we bought cost us 9,000 US dollars.
Wow. Yeah.
But we paid the price. We learned that it's a reliability issue
Mm-hmm.
because robustness. We launched that 2Cube in the space, and the only one works. The one with $9,000 onboard computer works.
You get what you pay
one,
for. Yeah.
The other one with the Raspberry Pi didn't work. Even we put the two Raspberry Pi, so they have some redundancy.
Yeah.
None of them.
Oh
works.
no, that's terrible. So when you're on a when you are launched among other Cube satellites, the way you described it, you were going to this International Space Station. So everybody's going to the same place. But I imagine sometimes they're launched freely into space, but then again, they would all be in the same plane, the same orbit, right?
Yeah.
So they just sort of drift apart far enough to be working separately.
Right.
And that's the disadvantage of being along for the ride. You don't get to pick your exact orbit.
No, that actually this industry is highly regulated. Before you launch, and you have a lot of regulate which orbit you can launch, and you have check within the orbit. You have check all the other satellite owners. They are already in there, and if there is a physical impact potential or risk, and also more importantly, it's a radio interference.
Oh,
So
yeah, of course.
You cannot operate satellite communication without a license.
That's interesting because are there international bodies that regulate that?
Yes, it's an international body, and each country has their organization. This organization is in Canada. It's run by the government.
I see.
So it's highly regulated, and you probably know that. I don't know if you know that. I didn't know before, because my students want to put a webcam on the satellite just for fun. We just look down and take images, and it turns out we need to get a license from the Global Affairs Canada.
Because I guess there's espionage concerns.
Yes.
Yeah, interesting. Let me switch gears a little bit. I was thinking to myself that your work has a thread running through it because everything's to do with tethers and fibers. I want to go to another fiber. I'll weave another topic in, and that is the research you're doing into using a tethered space tug to redirect asteroids. Can you talk about what that would look like?
Yeah, that is the second technology we are working. We assume you catch the debris with a robot, and then you have to process. You either just pour it and use the rocket you have and go down to the space. But there is a risk if you have a robot grab that big chunk of debris or dead satellite, and that dead satellite is kind of tumbling while it's uncontrolled. So you have to moving around. That poses a safety concern to we call the chaser satellite. So one way to address that is we have a small satellite deployed from the mother satellite with a little tether, like an anchor. You have then capture the debris and with a safe distance away with a soft tether link. So no matter the big one the big dead satellite is tumbling, I'm still away, I'm safe. Then once I capture that satellite, I using the control the force like you do the fishing, right? When you catch a fish, we pull the string to control the motion of the fish in the water. The similar way we do that to de-spin the satellite first, and then we pull the satellite into the position we want.
So let me see if I can echo that, because I'm not quite visualizing it. So if I'm in I'm not in it, but I'm in control of a larger satellite, and I deploy on a tether a robot that can grab the asteroid. So I'm still connected through the tether, but the asteroid could be spinning.
Yes.
And so first of all, the robot, we have to assume it's not spinning too quickly, or the robot can never catch it. So it's got to be a decent speed. So it catches it, but how do you prevent it from winding around the asteroid?
So it depends on how fast your mothership can respond to the motion. If you cannot respond very fast, so one way is we let this mothership synchronize your motion with the target. So we spin at the same rate.
Okay. So you would come to its North Pole or South Pole.
Yeah.
And then you would detach, and then the tether would just twist. It wouldn't whip around.
Usually we not. Usually it's spin. We just spin together. It's like we are in the equator orbit. We're moving with the tether, like the stage or stationary satellite, right?
Okay.
We're moving around, and then we deploy the tether, and with the robot hand, grab that astronaut, or maybe the harpoon goes into that capture.
Okay.
And then I try to slow down on my mothership and apply the force to the spinning asteroid, and use that way to slow down the mission, the spinning, and then we can pull away.
Okay. And that you know, in when I think about it, I think it's almost like trailer control. You know, sometimes the trailer can start whipping around, but of course you have a huge advantage on the Earth, which is friction. You have tires against the road, and eventually things will calm down. You must be using very well-timed bursts of thrust to counteract the rotation.
Yes.
I see. Okay. So, and then the goal of this would be to mine asteroids or prevent asteroids from hitting the Earth? What are you hoping to do with this technology?
Currently it's we want to do the space mining.
Okay.
Yeah. Get the space resource. And that one probably can relate to the next subject we're going to talk, the 3D printing in space.
Okay.
So that you get your materials from there.
Okay. Interesting. Yes. So I assume then that you're going to leave the asteroids that are coming to Earth that will destroy Earth. You're going to let Bruce Willis blow them up with a nuclear weapon. Is that a better plan?
That is not. I'm not thinking about that. For me, it's too big to stop, because currently we won't be able to kind of do that. And
no.
NASA, they have a scientist. They have a proposal. I don't know if you have read it on the web. They think they have a huge net. We deploy the net, then they can capture the huge astronaut and then pull it away.
And then pull it away. So you would rely on thrust to redirect it.
Redirect.
Yeah.
But imagine if there's a thrust big enough, can thrust the Earth, and how big the energy you need.
Absolutely. Well, I think the secret there is to see it early enough, right? So you don't have to deflect it too much.
Yeah.
So before we start talking about how we're going to convert these asteroids into 3D materials, let me ask you some. So again, this is another thread. This is another kind of technology, and it's carbon nanotubes. You've done research into carbon nanotubes in polymer, and you're taking advantage of a few properties there. One is that it has great tensile strength, but also that it conducts electricity. What are the interesting things you can do as a result of that?
Oh, that's a lot of things you can do. And this project actually was funded by Canadian Space Agency. They want kind of technology exploration. So one way for the spacecraft is to improve its efficiency, reduce its weight, right? Because you're probably 98%, if you launch one piece from Earth to space, 98% of the weight are the fuels.
Yeah.
So if you can reduce the weight, it's a big advantage.
Yeah.
So one way to do that is make the material multifunction. So one material can do multiple things. So carbon nanotube provide advantage of this. So I know that for the outside of the spacecraft, it's still the metal, right? Because you have a lot of the space environment, this oxygen, corrosion, this thing. So metal is still the better way to do that. But inside the metal, you sometimes you use some shielding material and those non-metal things. And if you, as a part of structure, secondary structure. So if we can make that material multifunction, that can save the weight. So for our project, our target is make a one super material. It is structurally strong. It can shield electromagnetic wave to prevent interaction. And you can shield the secondary radiation to protect the health of the astronaut inside the spaceship. And then it can electroconductive, so it can use as a sensor. So the material itself can self-monitor its structural integrity. If something crack, you can detect from the change of the resistance, right? Right. And also for the heat conduction. So you avoid for those polymer material because it's a heat insulator. The problem, you heat it, one end is very hot, the other end is still cool. So if you make it thermal conductive, it can dissipate heat evenly.
Oh, I hadn't thought of that. You're right. So so let's back up a little bit and talk about this. So most people are familiar with fiberglass, right? Fiberglass is just glass fibers in a resin. When the resin dries, it becomes quite hard, but also you can't pull it apart because of glass fibers. So this is just a more high-tech version of that. The carbon nanotubes. What is the definition of a carbon nanotube?
Yeah, carbon nanotube it's just formed by carbon itself, the carbon molecules, right? The carbon molecules is at that six side, right? The shape, and you make the tube that's very small. The diameter is about 1 nanometers, but for the length, you can several hundred or thousands of nanometers, and even longer. So the advantage is we use this small material because this carbon nanotube, it is very strong along its length direction, right? And also it has a very high ratio of surface to its dimension. So that means provided it's a good opportunity to bond with other materials.
Right. Interesting.
So,
okay.
Yeah, but for that advanced material, for the spacecraft, we don't use a fiberglass because too heavy.
Right.
We use a carbon fiber. It's very light.
Okay.
So carbon fiber it's big. So the carbon fiber, we use it to layer by layer bond it together. But those kind of material has a fatal problem. If you just hit like this, on the surface, you don't see anything. But inside, must be some crack between the layers, like a debonding.
Right.
So the bonding strength between the layers is critical to increase the bonding stress. So we put that small carbon fiber, a very small amount. You're talking about 2% to 3% in terms of weight percentage.
Right.
Around this surface, before we bond them together, we put them around the surface, spray them on the surface of the fiber, and we bond them together. In that way, we increase their peeling, shearing, and the bonding strength by 30 to 50%. It's very effective.
And you have the advantage that if you run a current through it, you can see it flex, and you can see if its characteristics are changing over time.
Yeah. Although the carbon fiber is conductive, but because you put the resin between, so there's no conductive between the layers. If we put the carbon nanotube there, we make the resin itself is conductive, electrical and thermally conductive. So then we can create the passage for electricity and the heat between the fibers.
Fascinating. And okay, so you mentioned earlier that it provides some shielding. Is it sort of like a Faraday cage, like the wire mesh on a microwave door that stops the radiation?
Stop radiation, but they have the different mechanism for the radiation shielding compared with the metal.
Okay.
For the metal, it's mainly the bounce back. You have incoming wave, it bounce back.
Okay.
Right. And for those material, it's not bounce. It's mostly through absorption.
I see.
For each, so you have to say a lot of layers within the sheet material, and the wave coming because the plasma is transparent to the electromagnetic wave. It's come in, then you hit these carbon layers, and it bounce back between the different layers and between the carbon nanotubes. So
this is fascinating because I just realized, one of the things that spacecraft often do is they'll go like into rotisserie mode, right? So that the sun is hitting them evenly and they don't wind up with stresses from that. But if you had carbon nanotubes in your construction, that would reduce the heat stress, wouldn't it? Because it would conduct it around the body of the vehicle.
Yeah, it helps.
So the two follow-up questions. One is, does it help with lightning strikes?
It helps, but not a lot because the carbon nanotube there, the conductivity is several orders smaller than the metal.
Okay, so it causes a lot of heat. Okay.
It's the capacity. It's not as good as metal.
Okay. And then the other question is this possibly a good technology for stealth aircraft or stealth vehicles? Because would it absorb radar, I guess is what I'm asking.
Yes, yeah.
Interesting. Okay.
And we did the test. It works quite well. And the second one I mentioned is we call the secondary radiation shielding. So the protons in the space will hit the spacecraft, the metal will pass through. The proton is very strong, it will pass through. But once it hit these metal molecules, it will generate the electron. It will hit the electrons. We call the secondary radiation. The electron will coming out. And in the past, the spacecraft design is used the metal inside another layer of the metal to shield those secondary radiation. But metal is quite heavy. Yes. So we put this kind of material, the polymer, basically the pure polymer, no fiber, carbon fiber inside. And we did a test. It's only about 5 to 10 centimeters, even that 5 to 6 centimeters. Oh, sorry, millimeters.
Millimeters, okay.
Of the material, very thin. And it can show, I forgot the percentage, but it meet the requirements. It's like for Earth application, it's for the doctors in the clinic, right? You're probably in the dental clinic. When they take the X-ray, the dental assistant will go to the other room and they cover you with a metal lead something.
Yes, yes.
In the future, you can have soft clothes with a soft plasma,
Oh,
a soft like a polymer stuff.
interesting. Okay.
Yeah.
So let me recap that. So if you're proposing a metal on the outside and the polymer with the monotubes on the inside,
Yes.
and when a proton hits the skin, the metal skin, it kicks an electron inside, which is absorbed by the inner layer.
Yeah.
Fascinating. Yes. Okay. So let me change gears again. And now we'll get back to what you were alluding to earlier, which is 3D printing in space, which, I mean, it's exciting to think about, right? Because it's almost like the replicator on Star Trek, you know, this idea that you can produce what you need, just you need the atoms, you don't need the parts, right?
Exactly.
So let's talk a little bit about what additive manufacturing is and how it works.
Yeah, additive manufacturing, it's like the printing. The old days you have inkjet printing. So additive manufacturing is kind of you print those materials layer by layers, follow the control, the pattern, and you build up material bottom up. So additive manufacturing, currently there are 3 ways. One way is traditional, you have those like a polymer, ABS plastic wires, you melt it and you inject the molten plastic, then they will bond each together and build up your solid structure. The second one we call the laser. So you have the powder there, you laser going through, you melt the powders and into the solids, and then you wipe out these powders, you lower your base a little bit, you put another layer of the powder on top of it, and you follow the same pattern. Okay. So this can be used for metal, right? And the third one is kind of liquid. You use a liquid polymer that is cured by some UV light. So you shoot the UV light, and they focus inside the resin. When it's cured within the resin, they pour it out.
Right.
So that's a 3 way to do the 3D printing with current technology.
So in my mind's eye, I can picture all 3 of those, and they all seem to rely on the presence of gravity.
Yes, you are right.
But they all have a disadvantage, or no, they don't all have a disadvantage, but definitely the first kind where you're just laying down material has the disadvantage. It's very hard to make an arch, for example, because as you get to the point where they're just dropping to the floor instead of attaching to your arch.
Yeah.
So I can see there being advantages and disadvantages to doing 3D printing in space. What are the types of things we can and can't do, or how do we adjust to the disadvantages?
Yeah. Currently, the people tried, like the NASA tried, and the ESA also tried. It's the first technology. It's the fuse and then deposit. Because you mentioned that that technology on Earth, they have the limitation when you print it. You cannot print those overhanging parts too much. You can live it. But because of gravity. Right. In space, you don't have the gravity. Mm-hmm. So you actually can do that. You can print in some like 90-degree angle. So you can print it that way. But the disadvantage, you also have it's for that one, because you build the material by bonding layer by layer. That gravity helped the bonds between the layers. Yeah. In the space, you don't have gravity. Mm-hmm. So your bonding stress is weak. And we did experiment on Earth. So we printed parts. For example, this is a pen. We printed parts along this direction. We bond this, and we pour this direction. They are very strong. because my fiber printed in this way, they continue this way, and then they bond each other. But
Right.
This was very strong. However, if I put in this way, it's very weak.
Like ears of corn. Like you can.
Yeah. So this is a techno, but for the other two techno, there is a challenge with the gravity. For the powder,
Yes,
you need the gravity to keep it on the working surface. On Earth, in the space, you don't have the gravity. So some people say, yeah, I maybe can put a metal part. So I use the magnetic field to keep it on the working surface. But that's only works for the ferrous metals, right? You have the metal part there.
No aluminum.
No aluminum, right? And for the resin, same thing. If you have a container of resin, in the gravity, the resin just goes everywhere.
Right. Yeah. Huh.
Yeah.
So it's a challenge.
It's a challenge. Another challenge is, for the 3D print, no matter which way, the heat is focused in the one point, concentrated.
Yes.
Right. Once you print it, the waste heat is dissipate, and so to protect the machine and the parts. So on Earth, you have the air. So the air ventilation takes the heat away. In the space, if you print it within the spacecraft, then you have the air. You use the ventilation, take the heat. But as you said, in the future, we want to build the spacecraft in vacuum.
Yes.
You have the heat management problem.
And what materials do you anticipate finding in asteroids that we would be building spacecraft with? Do we have iron, aluminum, all those things?
Yes. The current people have tried plastic, the first thing. Second is the titanium, the metal. Yeah, they tried.
But so that's what they brought into orbit to experiment with asteroids. What are asteroids made of? Do they have the material we need to make a spacecraft?
So that material, you can bring it from Earth, right? Or you're mining in the space. So the easiest way is catch the dead satellite, recycle.
Yes, I like that idea.
Yeah, and NASA, I think the DARPA, US DARPA, they already did that one. And then in the future, we actually can capture the meteorite and take the materials, and somehow you make it a powder, and then make it somehow you process it, and it can be used for 3D printing.
So another, you remember I sort of led with the idea that the exciting thing about 3D printing is you don't need to have an inventory. You just need material that you can make into tools or components. This applies to humans too, right? If I get my ear cut off in an accident in space, there's nobody around, like I'm not going to get a donor. There's no motorcycle riders in space. So 3D printing, one of the things you're looking into is the ability to print 3D human parts.
That's its long-term thing.
Yeah.
Yeah. This even, I don't know. The short-term I envisioned is you treat the astronaut like they have accident. The fire, they burn the skin, right? And so on Earth, it's very easy. You put the artificial skin there, and in space, right? If you have the bioprinting, we call it bioprinting, you can actually print the skin, and also the implants like the bone, the tools. This is it's already the technology is there. So printing the organ, it's another one. I think my colleagues and I, we propose something like a cardio vessel printing to repair your heart with 3D printing patch. But this is a long term.
Sure, but Keep doing that. We're all going to need these parts eventually. I love it.
Yeah, yeah.
Um, two final topics. They are related. One is this idea of using carbon fiber reinforced polymer for space structures. So we've talked a little bit about carbon nanotubes and how they can be used that way. But one of the really exciting things you can imagine using with very high tensile strength material is this idea of a space elevator. Can you talk a little bit about what a space elevator is?
Okay. The space elevator concept was originally proposed by a Russian astronaut. I think, what's his name? Tsikovsky, yeah. And in the 1895 or 98,
Wow.
right? And he said, okay, we can go to the space by climbing a rope. The idea is if you put a satellite in the Earth's geostationary orbit, that satellite is stationary relative to the Earth's surface. Then you lower a cable, you connect it, you can combine. But at that time, it was just a scientific fiction, right?
Right.
Nobody treated it seriously. And that situation changed in 1955 or 60. And the Italian space agency and the NASA, they worked together, launched the first tethered spacecraft mission. In that mission that was tested, you have a two-piece connector with tether, you rotate it, and they verify that way you can generate artificial gravity field. So over there, the people think, hey, tether in space is somehow not science fiction anymore. So people look at that concept again. You climb the tether into the space. But soon, once the engineer start to look at that problem, and they find that it's physically infeasible.
Right.
Because the tether has a weight.
Right.
If you use even the strongest material on Earth, the steel, high strength steel, and still the tether in the space won't sustain its own weight.
Right.
And also, in order to overcome the weight of the tether, you need a counterweight above the geostationary orbit. So that makes sure
to make sure it's in tension.
It's in tension, right?
Yeah.
Otherwise, the tether just collapse.
Right.
So because of that, even now, there's no engineer the material. It can be used to make that tether because they cannot support their own weight. Maybe in the future, we can make a rope from theoretically from carbon nanotube. If you can make a kilometers long carbon nanotube, then that tensile strength will be sufficient for that application.
Interesting.
Yeah. So overcome.
Yeah, go ahead.
Yeah, to overcome the limitation of that space elevator, because one end has to anchor on Earth. There's I think it's a Canadian scholars. They developed a concept called the floating space elevator or partial space elevator. Instead of one end anchor on the Earth, no, they have the two satellites floating in the space, and the tether can be to 20,000 kilometers long.
Yes.
And because it's a floating, and the tension within the tether is only the gravity difference between the two satellites. So that reduces the tension in the tether dramatically. And according to, I'm currently doing the study in this area. And according to our calculation and the existing material, it's good enough to make such space elevator.
So let me see if I understand that, because the classic space tether or a classic space elevator, one end is fixed on the ground and the other is in geostationary orbit, and there's a counterweight, but the destination is geostationary orbit. That's why it's tracking above where we are.
Yeah.
But the component on the ground is not in orbit. It's fixed to the ground.
Yes.
It wouldn't stay where, if you lift it, it falls because it's not in orbit, right?
Right.
It would have to be racing around the Earth to be weightless. So how does the lower satellite on that tether stay in position as it goes around, as both satellites go? Because wouldn't the orbit of this be slower than the one above?
Yes, before it is, but once you connect them together, it becomes a one piece.
So
it becomes a one piece. And then there's a tension between the two satellites within the tether, and the gravity will pull them perpendicular to the Earth, just around the Earth's radial direction. And their rotation is not geostationary. They can depend on the orbit. They can rotate faster than the Earth's rotation speed, like a satellite, right?
Mm-hmm.
And if they are high enough, they can rotate slower than Earth's rotation speed.
Okay. And so the idea is that I would launch a rocket to low Earth orbit and connect with the bottom satellite, and then I would have my payload take the elevator to the higher orbit?
To the high orbit, and then launch from there.
But wouldn't that have the effect of slowing down the pair of satellites that comprise the elevator?
Theoretically, it would not, if you assume that's a pure vacuum, right? And it's moving up, and whereas it's moving at the CG will lower a little bit, depends on the ratio. So if your payload is very small, the lower down.
Okay.
But then once you shoot the satellites, the payload up, and your CubeSat will move back. Sorry, your space elevator will move back.
Well, but if I do it often enough, the satellite pair, the elevator pair will start to have a lower orbit. I'll have to boost them back up.
Yeah, it would. You need to.
And I could use the Lorentz force. I could power it back up.
Electrodynamic Tether. Yes.
Yeah. You said something interesting in your work. Maybe you can explain it to me. The effect of the Coriolis effect. Mm-hmm. It's going to make as I ride the elevator, it's going to cause the elevator to kind of twist, right? It's going to cause it to bow.
Yes.
And I think in your proposal, you suggested, well, let's have two lines, and one is a down elevator and the other is an up elevator.
Yeah.
But that only works if you have the same amount of stuff going up as you have coming down. So how does that work?
Yeah. So it's interesting. You mentioned that Coriolis effect, right? It's going up, it's rotating the Coriolis force. It's perpendicular to your tether. So if you're fixed space elevator, so far your tether is strong, it just flow and it doesn't matter. But it's a floating space elevator. There's no anchor point. If you push too much, it will coming back, going this way, and then eventually it was tumbling. So the one way people doing that, they use the control. So I control the moving speed of the payload. So to control the swing angle. Okay. That's one way to do it. The two other way is I let 2 or 3 payload moving around the tether in the same direction, but at the controlled distance, and the control speed, you can do that.
Okay.
But it's not that efficient. So we propose that is our new proposal. So we propose a loop, two loop. So one going down, the force going that way. The other one going up, it was going that way. So they cancel each other. So the tether itself will bow a little bit, but the whole structure, it will keep in the vertical direction. And because it's going to loop, you don't have to stop going up, then going down. Right? You can continue doing this transportation.
Amazing. That I would love to see. So this has been a terrific conversation. I'm down to the last question. Thank you so much for your time.
My pleasure.
You have a very interesting body of work, and of course, you're doing lots more research. But are there areas of research outside your, related to space and orbital technologies that you're very curious about, that you think are really worth watching right now?
There's anything you can watch in the space. So the one thing is we are looking into to the deep space exploration. So we want to go to the Mars. We're already going, and we want to go beyond the Mars. And so there is a new technology people has developed for the deep space transportation. In the old day, it was solar cell. If you have a large cell, take the proton energy within the solar wind. But 10 years, I think 15 years ago, there's another new technology, which is called the electrical solar cell, E-cell. So it's similar like a tether. You have like a umbrella without the sheet. It's only just the metal frame, and each metal frame is positive charge, and then around that metal wire, it forms a electrical field. Then that proton, the positive charge in the solar wind, will be bounced back. So if you spin that layers or that wires, that you can form a continuous electrical field plane like a virtual cell. Then you harvest the energy in the solar wind from those positive charged part. So that can provide a much lighter structure and a much higher acceleration compared with the solar wind. And you can actually go to the deep space. So this is the one thing. It's really fascinating for this.
Absolutely. It connects with your other work, and because much of your work is about avoiding the need to bring 98% of your weight in fuel.
Yeah.
Right? Like so many of your projects are to do with how do we avoid needing fuel to accelerate a vehicle? So yeah, that is a fascinating project. It'll be exciting to see. Maybe we can go to Mars, but then we can also go to Venus and Jupiter.
This is what we call the fuelless propulsion.
That's terrific. Well, thank you so much, George, for being on the show. This is a great conversation.
Thank you. It's my pleasure to be here.
My guest today was Dr. George Zhu. A link to George's profile on York's website will be in the show notes. My name is Tim Hampton, and you can reach me at tim@unusuallywellinformed.com. Thanks for listening. I hope you will subscribe and join me for the next show with another unusually well-informed leader in business and technology.
Thank you for listening to the Unusually Well-Informed podcast. The opinions expressed by the host and guests on the Unusually Well-Informed podcast are their own and do not reflect that of their employer or any other affiliation.